So let's first define probability. What is probability? Probability is the study of randomness and uncertainty. So basically, it helps us quantify the likelihoods of different outcomes. It gives us a mathematical way to describe how likely something is going to happen. We also have something what's called an experiment. An experiment is any action or process whose outcome is subject to uncertainty. So some a few examples would be something like rolling a six-sided die. So that, for example, is a action where you don't know what the outcome is going to be. Something also like selecting a card from a deck. You don't know what card you're going to select. Or even something like, in a healthcare example, obtaining blood samples from a group of people. You don't know exactly what blood sample you're going to obtain from each individual person. That's uncertain. So those are a few examples of something what's called an experiment. Now, every experiment has something what's called a sample space. A sample space is the set of all possible outcomes in an experiment. So it's denoted by this big curly S right here. And as you can see, it's equal to something that is a set. So let's look at an example. Rolling a six-sided die. What are all the possible outcomes of rolling a six-sided die? Well, the sample space should be rolling a 1, 2, 3, 4, 5, and a 6. Similarly, selecting a card from a 52 card deck, the set of all possible outcomes should be every single card that's in the deck, so all 52 cards. So those are just a few examples of how sample space is related to an experiment. Now let's take a look at an example to kind of combine everything we've learned so far. So suppose we have three machines in a factory, and either one can be defective or not defective. And we'll denote those by D or N. Now let's list all the possible outcomes. So let's write out the entire sample space. The first outcome is they are all defective, so D, D, D. They can also be all non-defective, N, N, N. The first could be defective, but the other two are not defective. The first is not defective, and the other two are defective. The first two can be defective, and not the last one. The first two can be non-defective, and the last one can be defective. The first and the third can be defective, but not the second. And also, the first and the third may not be defective, but the second one might be defective. So that's our complete list of the 8 possible outcomes. What's really interesting is that we can actually double check that there are 8 possible outcomes by simply looking at how many possible states each machine has and how many machines we're evaluating. So if we take 2 to the power of 3, that actually equals 8. And you look at the 2 being the number of possible types of outcomes, and 3 being the number of things we're evaluating. In this case, it's number of machines. So if you look at that, you can see that it does in fact equal 8. There are 8 possible outcomes. So here we are looking at individual outcomes. But what if we kind of wanted to group these outcomes with some sort of mutual characteristic? That's getting into the idea called events. An event is a collection of outcomes from the sample space. Now, let's actually define a few events. Let's define event A as the first machine is defective. Let's call event B when the last machine is defective. So what would event A's set be? What would its sample space be? Well, let's look. DDD, the first is defective. DNN, DDN, and DND. In all of these outcomes, the first machine is defective. Now let's look at B. Last machine is defective. Again, DDD, NDD, NND, and DND. In all of these outcomes, the last machine is defective. And you can see that in these events, they are also made up of sets. And that gets us into something called set theory. Set theory lets us explore the relationship between events. So let's define something called a complement. In our case, we'll do complement of A. So A apostrophe. A complement represents all the outcomes that are not in A. In our case, we said that event A was the first machine is defective. So A complement would be the first machine is not defective. So let's see what that set would be. So we would have NNN, again, first machine is not defective, NDD, NND, and NDN. So in all of these outcomes, the first machine is not defective. Also in set theory, we have something what's called a union. A union, that's denoted by this kind of U thing right there. You would say it as A or B or both. So a union includes outcomes where, in our case, the first machine is defective, or the last machine is defective, or both. So let's take a look at what the set of A or B would look like. We would have DDD, DNN, NDD, DDN, NND, and DND. So all of these outcomes either have the first machine as defective, the last machine as defective, or both. We also have something what's called a intersection. In our case, the intersection of A and B, denoted by this kind of upside down U. And it would be spoken as A and B. So let's see in our case, what would A and B look like? This would mean the first machine is defective and the last machine is defective. So in what events in our sample space is the first machine defective and the last machine is also defective? Well, that would be DDD and DND. We also have something that's called a null event, denoted by this circle with a line across it. A null event is an event that contains no outcomes inside of it. If a intersection of two events is empty, so A and B is equal to nothing, then the events are called mutually exclusive. Also can be called disjoint events. What's really interesting is that we can actually represent set theory pictorially using pictures. Typically, we use Venn diagrams so we can kind of better capture the intersections and relationships between events. So here I'm going to draw a rectangle, which will represent the entire sample space, and the circles will represent events A and B. In notation, we typically draw an S at the bottom just to denote that we are drawing the entire sample space, representing the entire sample space using the Venn diagram. So let's take a look and see how we're going to pictorially represent the things we learned in set theory. So let's look at intersection first. So I'm going to draw my rectangle, and I'm going to draw my circles denoting event A and B. And I'm going to color in actually the overlapping region between A and B. And that will represent the intersection of A and B. So basically, all events that fall into A and B will be put in this intersection in the Venn diagram. Now let's take a look and see how we'd represent a union of A and B. Again, union is basically any event that falls within A or B or both. So you can see that I'm shading in both circles and the intersection of the circles to denote A or B or both. So now let's take a look and see how we represent a complement. So essentially every outcome that is not in event A. Again, we draw our Venn diagram. And we're going to shade everything that is not in event A. That also includes not coloring in the intersection of event A or B, because that also is a part of event A. Now finally, let's take a look at mutually exclusive events. How are we going to draw those? Well, essentially, we're going to draw two circles, event A or B, that will have absolutely no overlap. Because again, mutually exclusive events have no intersection between them. Their intersection is null.